Hello and welcome to today's panel discussion on low temperature solders. Low temperature solders are getting used in an increasing number of applications around sensitive components and other things. This panel is going to discuss today some of the methods for achieving that and what the benefits are with low temperature solders. To my extreme right we have Tseng from Shenmao. To his left we have Keith Sweatman from Nihon Superior. To his left we have Dr. Tevis from SAFI-Tech, and to my right we have Chris Bastecki from Indium Corporation. So welcome gentlemen, and thank you for joining me today. So I'm going to get straight in and I'll start with you, Watson, on the end there. So what do you think are the main drivers that are driving the demand for low temperature solders?
The biggest driving force nowadays is to reduce the thermal stress to the components, the BGA components. At higher temperature, it tends to warp and reduce the yield rate of assembly. So this is the biggest driving force. However, we also see some complex assembly with multiple reflows at different temperatures. So they would like to have a higher melting temperature at first, a medium melting temperature, and low melting temperature. This is another driving force to use low temp solder.
Right, okay. So Keith, would you agree with that? That package warpage is one of the key drivers?
Well, it's one of several, and I think it depends on the region. I really get the feeling that in China, the need to reduce energy consumption is a factor. Okay. That country has a program for energy reduction, and the numbers that you see for the energy saving made possible by reducing the process temperatures are significant. In the US here, avoiding of warpage in IC packages seems to be, and you get this strange phenomenon of hybrid soldering, seems to be more of a driving force. In other cases, say in wearable electronics, it's because you can use materials that are more temperature sensitive, that wouldn't survive normal temperature. So there are different reasons in different situations and in different markets.
Right, okay. Ian, have you any other areas that you think you can add to that? Any other drivers that you're familiar with?
No, we've heard the same things.
Okay. And I'm guessing you're probably thinking the same, Chris, unless you've got anything...
Very similar to what Watson
Right.
said.
Okay.
There are other incremental improvements, but I think the main drivers have been highlighted.
Good. So, my question to you, Chris, is the relaxation last year of the RoHS regulations to allow the use of bismuth, has that been one of the key elements to help you develop low temperature solders?
I think it's very beneficial to some of the solutions. When people look at low temp, the first thing they look at are bismuth tin systems, whether it's with silver or they add other dopants. So most of the low temp solutions where you get a reflow around 170 to 180 C encompass bismuth. So it's definitely led the way for that. So it's enabled that. But there are other approaches to it also that don't even need bismuth, but that's enabled that to move forward.
Okay, Ian, you're taking a slightly different approach, so I'm going to skip you on the bismuth question, okay, for a minute. Keith, what about the use of bismuth? I mean, what are you using for your low temperature alloys?
Well, I mean, really, irrespective of what RoHS has done, the options are very limited. If you look at the periodic table, the available elements that are known to be of low toxicity at least and have a melting point in the right range, if we hadn't have been able to use bismuth, I don't know where we would have gone. Right. Well, maybe my friend here might have offered a solution, taking a different approach. There are some other elements that we're looking at as well, which would permit even lower temperatures. But look, they had to release bismuth or we'd be stuck, really.
Right. Would you agree with that, Watson?
Yeah, we use a lot of bismuth and tin and some silver in our low temp solder, of course, with some other dopants. And the regulation from the rules doesn't bring any trouble to our product development. However, we're looking at the antimony usage because some companies they have a very high concern of the usage of antimony. So we try not to use this element in our solder to prevent the problem in the future.
Right. Are they using the antimony to offset the brittleness of the bismuth? Or
actually, if you add antimony in your solder, it doesn't bring the hazards to the environment. However, some oxide of antimony, they are not easy to be determined or measured. So some company decide to ban the antimony at all, so that they won't have any issue to determine this is safe, this is not safe.
Right. Okay. I mean, Keith, one of the issues, of course, with bismuth is it's very brittle. What are the best other alloys to add to this mix here to try and get better ductility or present the offset the brittleness?
The reality is there's nothing much you can do about bismuth because these dopants, to use a term I don't really like, that you add, don't really go into the bismuth. Really the only way I think that you can improve the ductility is to reduce the bismuth content to the level where the matrix of the solder is not bismuth but tin. And then you add things to strengthen the tin. So I think there's a bit of a misapprehension in that regard. And the problem is, of course, when you reduce the bismuth content to reduce its influence on mechanical properties, you start to go to a higher melting point and you get a pasty range. But it's one of these cases, as often in solder technology, where there's no good trade-off.
Right.
You're going to lose something to gain something. And so, people have to think of the additives as working on the tin rather than on the bismuth.
Okay. Ian, have you done any experience working with the sort of tin bismuth type alloys before you hit upon the current solution you've got?
Sure, definitely the first alloys that we worked on were bismuth-based because they are the lower temperature alloys. Like Keith said, there's not a lot of choices for there. And so our first products that we sent out for samples, indium tin bismuth and also bismuth tin. For our super-cooled product, liquid metal microparticles at room temperature ambient soldering process.
Okay. And what has been the indium approach, Chris?
Well, we have explored the common approaches with dopants and things like that, and it does work for some applications. But we just keep running into technical challenges where it just doesn't meet it. So, Indium Corporation's a material science company, and we challenge our PhDs to come up with some innovative ideas, things that are kind of out of the box you wouldn't think of. And there's a product that we're just announcing here at SMTAI, and it's a mixed powder technology, and it actually is bismuth free. Because I think we all agree that bismuth is very restrictive as a solution. So we're looking outside the boundaries of using bismuth. And
so you're using a mixed powder. You can't go beyond that to characterize what it is?
I mean, at times we do reveal, but it is patented now, and we do reveal that with certain customers and things like that. But it's we don't broadly announce it.
Right. Okay.
But it's a mixed powder. It's two different alloys we mix together, and the resultant solder joint has no low melt point phase, which is very critical to the reliability.
Right.
Because you don't want, when you reflow the first time, you can have low melt point phases, but when you reflow the second time, there better not be any around. So it's designed to make sure we don't.
Make sure you don't. What sort of minimum temperatures are you getting down to? How low are you getting?
So I guess with the bismuth tin alloys, you probably reflow in the 170 to 180 range. We're more like the 200 to 210 range. So we're up a bit, but it's
still less than what you're doing with current lead.
You're about 35, 40 degrees lower than your typical process.
Okay. So Ian, you've come out with a rather novel method for having a low temperature alloy by using an encapsulation system. Can you explain a little bit about how that works?
Sure. At SAFI-Tech, we're approaching the solder interconnect creation from a completely different pathway. So instead of having a reflow step and we're heating and melting the metal, we do all the heating and melting in our lab 100 miles away from where it's going to be used. So we make a supercooled liquid metal powder. So it's a microcapsule filled with regular solder metals, and it's got a special shell that forms on the molten metal, and then when we cool down that metal particle down to ambient temperatures, the shell protects that metal from the outside world, and it prevents that crystallization until you give it a nucleation event. And so we can bring this liquid metal and we can actually flow it at ambient temperatures, either using mechanical or a chemical dissolution process, and then form that solder interconnect without having the same heat impact that a high temperature reflow process would have, but still getting the same solder metal at the very end, so it would melt at the parent metal melting temperature.
Yeah, so once it's out of the capsule, then I assume it then reflows. If you were to rework it again, you'd have to rework it at the regular temperatures for SAC.
Yes, if you wanted to rework it, the metal would melt at 217, 220 and above.
Right. So, Keith, you touched on earlier some of the benefits for driving heat out of the process, for getting the low temperatures. Energy is obviously a big one. It's a huge saver in the factory. What other benefits would you get? Would you need, potentially smaller reflow ovens and things like that, so you're not using up as much factory space with these massive ovens?
Well, yes, all of those factors in some markets are certainly the driver. Again, I think you've got to segment the electronics market into different categories, high reliability and whatever. I can't really see the bismuth-based low melting point alloys being used in high rel applications because it's very hard to get away from the intrinsic limitations of the bismuth system. I mean, if you recall in the period when the industry was looking at finding lead-free solutions, when we had to get rid of lead, tin bismuth didn't stay on the short list for very long because in terms of what the market was expecting then, it just couldn't match. So it's interesting in a way that there's been a change of attitude in that period since the transition to lead-free and now, where we're saying, look, maybe in some applications we don't need such a strong, reliable joint as we thought we needed.
Right.
It's like it's a downgrading, you might say, or you could say more positively, it's not delivering any more reliability than the product really needs. And I noticed that the biggest use of these low melting point solders at the moment is sort of in intermediate reliability level products, where obviously the industry sees advantages in compromising. Right,
okay. Interesting. Watson, I'm going to change the subject a little bit and move on to another topic that's hitting the headlines at the moment, which is in the semiconductor packaging world, something called heterogeneous integration. Can you tell us what heterogeneous integration is in your view, and how what it brings to the packaging form?
The heterogeneous packaging helps to reduce the size of the packaging and also to shorten the distance between the circuits. So if you are doing high-speed communication between the circuits, it's a very good technology. And also it decreases the size of packages. So if you have like portable wearable devices, you need a smaller package and you can use this technology. However, the disadvantage is the heat generated from the different chips. So the package itself needs some special design to get the heat out so that it can work.
Is the compatibility of the materials used inside the package, would that be part of this heterogeneous integration system, where there's less mismatches with materials and this type of thing? Or is it simply a geometric phenomenon?
Right now, we think the biggest challenge is how to get the heat out the package. There are many different ways you can use the tin materials to get heat out, and also at the same time to make the size of the package as small as possible.
Okay. Keith, have you had any experience with this?
Well, you know, we have this new term has been introduced, but really it's just a continuation of what's been happening in the industry for decades, really.
Right.
It's just packing as much as possible into a single substrate or into a single package. So it's a new term, but it's really not a new issue. And,
right, it's true.
yeah.
Somebody said to me earlier this week, it's just a multi-chip module.
Well, exactly. That's what I'm saying, yeah. And I mean, the challenges remain the same. As you say, when you're mixing different materials, you've got CTE differences, and the CTE differences are the killer in all of these things. So you've got to look at different materials, redesign, heat management, things like that. So it's just a new name for a well-established trend.
Right, okay. Okay, so do you think there's any work being done on, I mean, how can I put this? Indium Corporation has a lot of information about how indium solders work with indium underfills and other materials within a package. Do you think there's ever going to be any work done to try and make the body of knowledge expand so that manufacturers can learn how an indium solder is going to work with a Henkel underfill and this type of thing?
Well, you bring up a big challenge of heterogeneous integration. So from our standpoint, we work on what we see, a big trend is a lot of solder paste being used. And it's going to very fine powders. We're going to type 6, type 7 powders, and that's how, you know, we have to meet those needs. And we do have to be very concerned about the residues. The pitch is getting so fine, it's very hard to clean the residues off.
Right.
So that's one phase of it. The other is when you're looking at flip chip fluxes, you know, there's a trend toward no clean rather than water soluble. That's a big change. And you have to make sure that the no clean flux residues are compatible with underfills and things like that.
Right.
So we do a lot of work in that area, and we have to work cooperatively with, you know, with
other companies. Yeah.
With other companies.
Coatings.
So that's driving the work that I see is transition to very fine powders, type 6s, type 7s, and transitions from water solubles to no cleans and compatibility issues.
Right.
All fun technical challenges.
Absolutely. Yeah. So would you agree with that, Watson? Do you think you're going to see more cooperation between manufacturers on materials so that we can get material sets working together better and having less issues?
Yeah, we see the industry now needs many different kind of materials. Not like the old days. You have one product and which is suitable for most of the applications. Nowadays, we have to develop the different applications, just like Indium do. We must have a high melting temperature, medium melting temperature, low temperature, and different fluxes, no clean, water soluble, and low residue for different applications.
Right.
This increase the complexity of our product lines.
Okay. Well, anyway, gentlemen, I think we're starting to run out of time, so I want to thank you all for joining us today. It's an interesting topic. I think the work on low temperature solders is going to continue and will become a bigger phenomenon probably going forward. But for now, Watson Tseng from Shenmao, Keith Sweatman from Nihon Superior, Ian Tevis from SAFI-Tech, and of course Chris Bastecki from Indium Corporation. Gentlemen, thank you very much, and thank you for joining us today.